We speak of the inverse of a matrix as if every matrix has one. The truth is brutal. Almost no matrix earns a real inverse. Out of all possible matrices, one rare condition grants a genuine two-sided inverse. The answer hides in a single number, the rank, and in a beautiful geometric picture built from 4 fundamental subspaces. To pass through the gate, a matrix must satisfy a strict demand. Its rank R must equal both its number of rows m and its number of columns n. Only a square matrix of full rank slips through and claims a true inverse. To see who passes this test, let's meet the players. Every matrix, capital A, has m rows and n columns. Its rank, written as R, counts the number of independent rows, which always equals the number of independent columns. These three numbers, m, n, and r, decide everything. The whole story comes down to how R compares against m and n. Every matrix lives inside 4 fundamental subspaces. On the input side sits R to the n, the space of all possible inputs. This input space splits into 2 pieces. The first is the row space with dimension R. The second is the null space with dimension n minus r. These 2 subspaces are orthogonal complements. They meet at a perfect right angle, and together they fill the entire input space. In other words, the dimension of the row space plus the dimension of the null space equals n. The null space holds every vector that A crushes to 0. So when that null space shrinks to nothing, no input is destroyed. On the output side sits R to the m. It also splits into 2 orthogonal pieces. The column space with dimension r and the left null space with dimension m minus r. The left null space is just the null space of A transpose. The matrix A maps the row space directly onto the column space, while it sends the entire null space to a single point, 0. The dimensions of all 4 spaces are governed by that one number, as R. Now that these spaces shrink and grow with R, let's see exactly what R decides. The first case is the special one, R equals m equals n. The matrix is square and full rank. Both null spaces collapse to just the 0 vector. Nothing is crushed. Nothing is missed. Every input maps to exactly one output, and every output traces back to exactly one input. A perfect bijection. Here A itself is invertible with a true two-sided inverse. Second case, R equals n, full column rank, which describes a tall matrix. The null space of A is just the 0 vector, so the map is injective, meaning no input is lost. But the left null space is not trivial, so the map cannot reach every output. This means only a left inverse exists, and it is given by the formula, the inverse of A transpose A times A transpose. Notice the key piece here. The matrix that's actually invertible is A transpose A, which is an n by n matrix, not A itself. Let's check it works. The inverse of A transpose A times A transpose times A collapses to the inverse of A transpose A times A transpose A, which equals the identity. So for a tall matrix, A transpose A is the small invertible one. Let's make this tangible. Take A as the 3 by 2 matrix with rows 1, 0, 0, 1, and 1, 1. First compute A transpose times A, the result is 2 by 2. The top row is 2, 1, and the bottom row is 1, 2. Its determinant is 2 times 2 minus 1 times 1, which equals 3. Since 3 is non-zero, A transpose A is invertible, and the left inverse formula gives the identity on 2 dimensions. Now compute A times A transpose. This one is 3 by 3. The rows are 1, 0, 1, 0, 1, 1, and 1, 1, 2. But notice that the third row equals the first row plus the second row. So its rank is only 2, which means A times a transpose is singular. The left inverse works, but no right inverse can exist. Third case, R equals m full row rank, a wide matrix. Now the left null space is just a 0 vector, so the map is surjective. It reaches every output. But the null space is non-trivial, so many inputs collapse together. This means only a right inverse exists. It is A transpose times the inverse of A times A transpose. This time, the invertible piece is A times A transpose, which is an M by M matrix. So for a wide matrix, A times A transpose is the small invertible one. This is exactly the opposite of the tall case. Fourth case, the rank R is less than both M and N. Now both null spaces are non-trivial. Information is lost on the input side and outputs are missed on the output side. No clean inverse exists at all. The best repair here is the pseudo-inverse, written A+, built from the singular value decomposition. And note this clearly. A left inverse or a right inverse is not a real inverse. Each one works on only one side, and each relies on a different smaller invertible matrix, never A itself. Notice the pattern. Every case is really about one thing, information. A non-trivial null space means that some inputs get crushed to zero, information is destroyed, and it becomes impossible to recover. A non-trivial left null space means that some outputs are never reached. Only when both null spaces are trivial, which happens exactly when the rank R equals M equals N, is no information lost in either direction. That is the only condition that allows perfect reversal. Being square alone is not enough. A square matrix with dependent rows still has a null space and therefore no inverse. This single insight unifies solving systems, least squares fitting, and the pseudo-inverse into one continuous story. The true two-sided inverse is the rare special case. The one-sided and then pseudo-inverses are nature's graceful fallbacks.